Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media. We started discussing about the three-phase flow through porous medium, and where there is exchange, there is interaction between liquid and gas. So, we had there is a phase equilibrium involved, which we try to simplify by the use of these formation volume factor terms and solution gas oil ratio. So, let us see how what we defined in this case. We had already talked about these formation volume factors for oil, water and gas and solution gas oil ratio. We had talked about stock tank condition and reservoir conditions, what these are. If we try to draw this would appear like this. If we look at the density at reservoir condition, so density of oil at reservoir condition, similarly density of water at reservoir condition, density of gas at reservoir condition. So, density of water at reservoir condition would be density of water at stock tank condition divided by formation volume factor for water. So, this is how the relation works out, right, because formation volume factor was for a fixed mass of, say if I look at the water, which is the simplest, for a fixed mass of water, the volume under stock tank condition or volume under reservoir condition divided by volume under stock tank condition, right, volume under reservoir condition divided by volume under stock tank condition. So, this is what is. So, we can write density under reservoir condition as this. Similarly, one can write density of oil, but here this additional term solution gas oil ratio and density under stock tank, density of gas under stock tank condition, these also has to be accounted, because this much of oil is also present in reservoir at reservoir condition. Okay. So, this is how rho, rho w, rho g under reservoir condition, at reservoir condition, these are the terms. So, now if one tries to write volume balance equation under stock tank condition, that means all the volumes are expressed under stock tank condition, then one will write this is the volume balance equation, and you can see here we are adding some term QO, QW, QFG plus RSQO. So, this first equation is for oil, second equation is for water and the third equation is for gas. Okay. And this QO, QW, QFG plus RS, this is these terms. So, QO, QW, QFG, they represent volume of oil, water and free gas. QFG is free gas. QFG is free gas produced at stock tank or standard condition, per unit time per unit reservoir volume. So, volume withdrawn from the system, that means when we draw differential element here, we draw differential element, we talk about a pore space here, and these pore space is now we have separated into three compartments. One is SO, another is SW, another is SG. Okay. So, now these three compartments, and now I have continuity going in. So, there is flow of oil, flow of water, flow of gas, and because of that these saturations they are changing with time. We have already done it for two phase system. We showed that Mx, you remember what we did that time, Mx at x, Mx dot, we wrote Mx dot, mass flow rate, mass flux in x direction minus mass flux in x plus delta x direction, and that was delta S W that was equated, and we had done this in earlier lecture. So, we are doing that same exercise here, we are doing the same exercise here for the three different phases, and so now this is oil is flowing, correspondingly its saturation can change with time, water is flowing, correspondingly its saturation can change with time, gas can flow and its saturation will change with time. Obviously, the sum of these three saturations, that has to be 1. So, that the total volume, because total void volume is not changing, that remains same whatever complication you add. And suppose I have some way to produce some oil, water and gas from this grid, from this differential volume, and let that be QO, QW, QFG. QFG is a free gas, because you are producing both free gas and dissolved gas. So, QO, QW, QFG, they represent the these elements produced. So, this is the volume produced. So, volume means now we have volume at what condition, that is important. Volume can be under two conditions, there will be two different volumes. So, one is at stock tank condition, another is the reservoir condition. So, volume at stock tank condition or standard condition, per unit time, per unit reservoir volume, that means this total volume we have. So, per unit reservoir volume also, that unit is there. That is, I think, the unit of this continuity equation anyway. All these terms are volume per unit reservoir volume, per volume per time per unit reservoir volume. So, this is what these terms are all about, because this was, see, look at it here, this is basically this is the accumulation term del del T of 1 by BO phi SO. Okay. So, phi SO, okay, generally we had the density term here. So, then we would have talked about it as a mass, right, but instead of density we are having 1 by BO, and BO is not a density, right. BO is basically just a conversion factor from the reservoir condition to stock tank condition. So, this is a conversion factor. So, density term I am not considering, only thing is I have taken everything under same pressure temperature condition, which is the stock tank condition. So, that is the job of this BO, BW and BG. Okay. So, this is basically the continuity equation, and one can now see that this is 1 by BO UO, okay, this is UW, and this is UO plus 1 by RS by BO UO plus 1 by BG UG. Here the accumulation term is also both in the oil phase as dissolved gas as well as in the gas phase. So, this is a little complicated, but this is the relation for the gas phase. So, one is supposed to solve these equations now when it comes to the three phase flow, and this is the simplest way to explain. I mean, if you do not want to consider this BO, BW, BG, then you have to bring in the PVT relationship as it is covered in phase equilibria thermodynamics. The conservation equations in terms of pressure gradient, that means here we had only UO 1 by BO UO 1 by BW UW 1 by BG UG, those kind of terms were there. These are accumulation terms we have already seen, and this is the volume produced. So, these two terms are as it is, we kept only this here instead of this UO term. Now, we are writing instead of UO as lambda O grad of PO. We can understand very well, because this is Darcy's law. We know superficial velocity UO would be what? UO would be minus KRO divided by mu O into grad of PO. So, that would be the superficial velocity. So, what did we have here? We have inside this bracket, there was a minus sign outside, 1 by BO UO, right, and UO is this quantity. So, that is why, and further one must note here that it could be only grad of PO, or if there is any other than pressure, if you separate out the pressure and the gravity head, okay, then one can consider the driving force. So, if you consider pressure here separately from the gravity head, then there would be another term which is rho g z, because pressure you are applying, and plus there is a rho g z hydrostatic head also operational for the flow. So, this is customary to put this. So, it is one can consider this as well instead of just simply grad of PO. So, that is what you can see here. Rho is rho of oil. So, that is exactly what you see here. Lambda L is KRL by mu L BL into K, KRL K KRL by mu K KRO by mu O BO. That is exactly we have K KRO by mu O, and BO was originally there anyway, 1 by, it was basically 1 by BO into UO. So, here also it would be 1 by BO would be there, this term. So, then this is true for the Lth phase. So, for oil phase this would be true, and there would be additional it could be just, I mean, see, when we are having a horizontal flow through a core, we are talking about delta P, but when there is a 3-dimensional flow, one needs to have one may have to consider the gravity. Otherwise, you have to account for it in the pressure itself somehow. Either you do it explicitly or implicitly one can do it. So, this is the simple expression one can have, and you can write this in terms of lambda, where lambda is, this is the definition of lambda for the Lth phase, and this lambda is referred as mobility. And also this gamma is basically the specific weight. So, gamma is basically rho g term. Okay. So, rho g z, so grad of rho g, grad of PO minus rho g z. So, that is why you are writing it as grad of PO minus gamma of oil grad of z, gamma of water grad of z. Okay. So, this is what the equation becomes. So, now you can see there are basically 6 unknowns: PO, PW, PG and SO, SW, SG. These are the 6 unknowns one has, because BO, BW, BG, the formation volume factors, and RS, solution gas oil ratio, these would be known a priori. That is the understanding. This has to be tested. This has to be tested in the laboratory, and one has to find out. So, 6 equations. So, you have already, I can see there are 3 equations. You need 3 more equations. Okay. So, then you have this cycle completed. So, we can see here that you have unknowns SO, SW, SG, PO, PW, PG, and so you already have 3 continuity equations. Other than that, you need to have 3 additional equations, and those are, one is this sum of the 3 saturations, that has to be 1, and then there would be one equation, capillary pressure between oil water, capillary pressure between oil gas. So, these has to be PO minus PW, and this is F of SW SG, and P capillary pressure oil gas would be again function of SW SG, because SW and SG moment these are specified, then SO would be automatically specified. This is 1 minus SW minus SG, because sum has to be 1. So, and this BL, the formation volume factor, and for that matter solution gas oil ratio, that has to be known a priori. So, now to solve these equations, there are some unique techniques available. For example, one can look into this method is a very well known algorithm. Lot of work has been done, and still people use it in many, even for research purposes. Full form of this is implicit pressure, explicit saturation. So, that is why this IMPES. So, that is the full form, implicit pressure, explicit saturation. This IMPES method here, the one simplification is done in the sense that these as the time marching, generally this kind, whenever you have such kind of continuity equation, you will first of all you will break it into finite difference, right. If you are familiar with finite difference, you will be able to appreciate that you can, if this is the x grid, if this is the x grid, then one can break it into hundreds of such grids. Okay. So, one can break it into hundreds of such grids, and then at every grid you are putting some values of these unknowns, and then you take one delta t time step, and all these derivative terms, they would be basically, you have, let us say, a profile of pressure. So, you will consider this pressure to be constant over this grid, constant over this grid, constant over this grid, like this, and since you are breaking it into 100 such grids, so then automatically, in an overall sense, you will find there is a continuity and it looks like a continuous function. So, one can use finite difference. So, find out what it is at certain time, all these hundred or thousand grids that you form, and then track it. You give one delta t time step and do all these changes, assuming that over this time step things are linear. Okay. So, as if you can go for a Taylor series expansion and ignore higher order terms and consider these only the linear part, only the first order term, just with the assumption that the delta t that you have chosen is very small, delta x that you have chosen is very small. Okay. So, you continue to march like this in time and find out the solution at certain other time that you are expected to, that you are looking for. So, in this process, see, one can see, you can see, for example, in the continuity equation, I had that lambda term just in the previous slide. Now, this lambda term has the permeability term, relative permeability term, Kr. Now, Kr is a function of saturation once again, and saturation itself is an unknown. So, are you going to solve everything simultaneously? Then the computational load would be more. Probably a prudent approach would be that, okay, at this time step I find out what are the saturations are, and then based on these saturation values I can make a guess of those permeabilities for the next time step and use those directly. I mean, so I do not keep this, I simplify this. Okay. So, and then after I complete this time step, then I update the relative permeability values, etc. So, this kind of simplifications one can do, and this kind of simplifications are acceptable with the assumption that this delta t is very small. So, over this delta t, the saturation change is anyway small. So, that effect of that on relative permeability can be ignored. Okay. And then after you complete the time step, anyway you are correcting it. Okay. So, you are not simultaneously solving everything. So, out of that urge that I do not want to complicate, I want to keep things simple. So, this kind of techniques became popular, and this kind of techniques are still today, it is extremely popular in many such simulation of three-phase system in porous medium. On the other hand, one can go for simultaneous solution or sequential solution, which are more rigorous, so to say. There are many simulators available. Before I go to simulator, I must point out that there is this scope for solution in more than one dimensions. Solution is more than one dimensions in the sense, here we talked about in this continuity equation only one x. So, it is a one dimensional problem, three phase flow, but one dimensional. But in a real porous medium, I mean, if you want to solve it for a real reservoir, you may have to resort to 2 dimensions or 3 dimensions. So, then in that case one has to go for, so the dimension will change in the sense these equations, it will not be, here we have to consider the dimensions of x and y and z, all these dimensions have to be, so it would be del p del x, del p del y, del p del z. So, those type of terms have to be considered. So, in that case you can show in fact that one would, if one looks for a solution, then there is, I mean, we basically when you try to solve these by finite difference, you go for an algebraic, basically it becomes, this entire problem becomes algebraic, because you break down into linear, you linearize this entire problem, only work with the first order term. So, you convert this one set of partial differential equation to algebraic equations, which are probably thousands of them, okay, and solving those simultaneously. So, there, and when it comes to solving those equations, generally one resort to something like a matrix. So, it would be a matrix and then a vector which you want to find out, and then another column matrix. So, this you want to find out these. So, generally there are ways to solve these. Now, when it comes to two dimensional problem, then there are some unique ways to order these equations, and they have a lot of finesses they put when it comes to solving these problems for more than one dimensions. So, these are some of the things which is covered in reservoir simulation, fundamentals of reservoir simulation, but I just wanted you to appreciate that these kind of simulations in multi dimensions are done with this set of equations, and these are commonly referred as black oil simulators. There are commercial simulators available for this purpose, and more developed simulators are these days, because this is leading to reservoir simulation, and reservoir simulation is a very well established subject by itself. So, there are a lot of proprietary softwares available in this area, where at the heart of it, these continuity equations and relative permeability. So, these informations are to be put as an input to the reservoir. I mean, these, say for example, relative permeability curve and all, but there are a lot of other graphics, and but the essential treatment would be very similar to what I mentioned, because at the end of the day one has to solve the continuity equation for the three phases. May not be only one dimension, maybe two or three dimensions. Okay. Maybe there would be a fracture in the middle, so one has to account for that. So, there would be a fracture permeability. So, there will not be a single permeability, there will be a layered reservoir. So, there would be layered multiple permeabilities for different zones. So, those complications will come in there, and so there would be portals for doing those, but the heart of those simulators are these equations that I mentioned. So, with this background, just I briefly try to mention couple of things here. One is that if somebody works with these compressible single phase fluid, in that case it is a single phase fluid. First of all, this is something which is not a three phase or two phase system, single phase fluid, but slightly compressible. So, what that means is that same equation I had written earlier, I had written only for one phase. I have written it for three phases earlier for the continuity. The same equation is written here. Instead of BO, BW, BG, only B is given, because we are talking about, because this is a lot of times you can treat this oil or whatever is inside in the reservoir as oil with some amount of gas inside, and we can treat this fluid as slightly compressible, single phase slightly compressible system. So, then one can have the formation volume factor for that single phase. Now, compressibility is defined as this quantity from basic physics. So, this is in turn is 1 by rho del P at constant T. T is temperature in absolute scale. So, this is considered, Cf is considered constant over the range of pressure of interest. So, if one does the integration of these, then one can write this density as this quantity, rho is equal to rho 0 e to the power Cf p minus p 0. So, what I am essentially trying to say here is that BO by B is rho by rho O. We have already looked at it, that is the definition of formation volume factor, and which is simply e to the power Cf p minus p 0. Now, the term slightly means this Cf is small, and Cf is small means if Cf is truly small, then I mean, suppose I can, first of all, e to the power Cf p minus p 0 can be expanded in this form, in a series form, and then we can say that we can ignore higher order terms with the assumption that Cf is small and Cf square and all, they can be neglected. So, now here I must write rho, I must mention rho is the density at reference pressure PO, and this is reference pressure PO, not rho oil. and BO is the formation volume factor of the single phase at PO. So, that is that. So, this PO should not be confused with this rho O is at pressure PO, reference pressure. This is not rho oil, that one must note. PO and rho O, these are the reference conditions. Okay. So, this is how we can write this BO by B. So, bottom line here is, if CF is small, then in that case, so if CF is small in the sense that if CF is between 10 to the power minus 5 to 10 to the power minus 6, so terms of second order onwards can be neglected, and then B by BO was that thing, right, rho by rho O. So, from there it is, one can write B is equal to BO by 1 plus CF into P minus PO. So, in that case, del T of phi by B can be expanded in this form, and if one considers CR as the rock compressibility, so then one can write the porosity phi. If one considers rock to be compressible, that also there is a possibility, then one can write this phi is equal to phi 0 into 1 plus CR P minus P 0, just like the way we had written earlier for, if we look at this B by B, that is the density. When we found this density with the CF, how was it written? Density is rho by rho O. So, rho by rho O, that is equal to 1 plus CF P minus P 0, because you are ignoring the higher order terms. Okay. So, rho is equal to, you are writing rho O into 1 plus CF into P minus P 0. Rho O means rho 0 into 1 plus CF into P minus P 0. So, by the same token, one can write phi is equal to phi 0 1 plus CR into P minus P 0, where the CR is rock compressibility. And further, if one can neglect, we had already a gravity term, that gravity, suppose I build it in pressure, I do not need to bother about gravity. If we ignore this CR, consider this to be 0 and some other simplifications, one can write this becomes the governing equation for the pressure profile for a slightly compressible system. So, this is also a very useful equation here, because if you, instead of talking about oil and gas and two phase flow and all this, if you can treat the fluid as slightly compressible fluid, and if you can probably that can predict the pressure profile much better or in a much simpler terms using these equations. And here we are writing it is Q with a tilde, because Q tilde is now not volumetric flow rate as we had done earlier. Q tilde would be the mass of gas produced per unit time per unit volume of porous medium. Okay, so, this is the master equation, and in fact, one can solve analytically. There are analytical solutions available in Kerr's law and Ziegler for similar equation. So, this is a very good way to treat oil and gas and dissolved gas and their mixture as a compressible fluid, if one can, if that is permitted. That means, if provided CF is in this region, the compressibility is in this region, one can solve this equation also. So, this equation you can see you have the CF term already inside. So, it has compressibility inside. Okay. So, it is basically the pressure equation. So, one can solve the pressure profile. And also I must point out before I close this chapter that this, if somebody looks for the general equation for gas flow, then this is the regular continuity equation that we had, but then the density has to be written as P m by Z R T, where Z is the compressibility factor, because you know that we write it as P v is equal to N R T. So, now this is for the ideal gas law, but one has to bring in, or for 1 mole it would be P v equal to R T, but we have to bring in, if it is a real gas, this Z is equal to PV by RT, which is for 1 mole it is basically PV is equal to RT is the ideal gas law, but instead of these one has to consider PV is equal to ZRT when it is a real gas, where Z is the compressibility factor. One has to find out this Z from the compressibility factor chart, where compressibility factor is posted as a function of reduced pressure, which is basically the existing pressure of the system divided by the critical pressure and at different temperatures T in absolute scale divided by critical temperature. So, from this chart one needs to find out what is the Z. Z is 1 for ideal gas, but for real gas it could be much smaller. It depends on what pressure and temperature the system is in. So, one has to find out this Z from this compressivity factor chart or some other digital method, may not have to read it, but digitally transfer it, and then consider these in this equation for single phase flow. Here the density term wherever it is, now it would be, since it is a compressible system, this rho is to be considered here, and that rho term will come here, and rho has to be considered following this equation. Okay. So, then this becomes the master equation for flow of gas through a porous medium. Okay. So, using this compressibility factor term. So, this is something which I must mention, that if for a gas flow such treatment, such treatment is also there without considering the formation volume factor. So, this is all I have as far as the this immiscible flow or multiple phases flowing through a porous medium is concerned. So, I have already talked about Buckley-Leverett method and the analytical treatment, and then I try to show basically the treatment of Buckley-Leverett, the solution of continuity equation in the analytical and graphical mode, or using geometrical construction. Instead of that, here I mentioned about various if somebody has these resources, computational resources at their disposal, they can solve this continuity equation along with these parameters. So, this is the way to handle 3-phase flow in a porous medium. So, this is all I have as far as this lecture module is concerned. From next lecture, I will be talking about some other topic altogether, not this immiscible oil water gas flow through porous media. Thank you very much.